What does a technician say if he's been troubleshooting dynamic multi-point VPNs all day long without success? The answer is, those DM VPNs. Well, in this video, you and I are going to take a very structured, logical approach to identifying the challenges with DM VPNs and then systematically troubleshooting them step by step. Let's jump in. I'd like you to imagine that you and I have been called in together to assist this company in troubleshooting their DM VPNs. So one of our strategies that you and I are going to use is we're going to ask lots of really great questions. For example, has this ever worked? Or what part of your DMVPN network is functioning? And based on the answers to those questions, we learned that R3, R4, which are both acting as spokes, and R1, which is the hub, are currently working perfectly. Now that's really important because regarding verifying the configuration and the keys and IDs and so forth, we can just use R1, R4, or R3 as a template as far as a known good quantity because those are currently working in the DMVPN. Now, if they told us that R2, for example, is a brand new spoke, it just got installed, they can't get it working, we've just isolated our fault domain to R2. So a couple of things we would do, we'd want to verify basic connectivity between the address of R2 and the address of R1. They have to be able to talk to each other if we want R2 to register and subsequently build the GRE connection between R2 and R1. So tools we typically use for basic connectivity are ping. Now ping behind the scenes uses ICMP. Now if there's a firewall on the internet that's blocking ICMP, a ping may not work. And that doesn't necessarily mean that we don't have connectivity, it just says we don't have connectivity for ICMP. But ping would be a great way to just test basic connectivity, assuming ICMP is allowed. We could also use the command of traceroute to verify the path between those devices. And that also can verify connectivity end-to-end. And what's notable here regarding basic connectivity is that for DMVPNs, we're going to need to make sure we have two protocols that are allowed through. UDP, User Datagram Protocol, port number 500, because that's what IKE Phase 1 by default uses to negotiate. You might also want to double check that 4500 is also allowed. NAT Traversal operates at port 4500. And also protocol number 50, which is IPsec ESP. And that's the layer 4 protocol. So you'd want to make sure the entire path between R2 and R1 supports UDP port 500 and protocol number 50. In addition, we'd also want to make sure those two protocols are also supported in between R2 and R4 and also between R2 and R3. Because in DMVPN, when R2 starts talking directly with R4, the IPsec profile on the tunnel interface is also going to try to encrypt that traffic, which will initiate the IKE Phase 1 and IKE Phase 2 between R2 and R4, and R2 and R3, which will also require UDP port 500 for the negotiations of IKE Phase 1, and also protocol number 50 for the actual IPsec traffic itself. Now, one of our challenges is that in working with this network, if it is in production, we don't want to do damage to the current connectivity that these devices are all sharing with DMVPN. However, if we were in an environment like a lab environment, one of the things we could do to troubleshoot was to remove the actual IPsec profile off of the tunnel interface. So when that's possible, for example, a lab environment, or if the entire DMVPN is not working at all, by removing that IPsec profile off of the tunnel interface of R1 and R2, we could in one fell swoop remove all of the IPsec and cryptography stuff as part of the problem. Because once that tunnel profile is off of the interface, if it's still not working, we have a more fundamental problem with DMVPN. It's not the cryptography that's causing the issue. Now, on the other hand, if we take the IPsec profiles off of the interfaces and it starts to work, that also helps identify the fault domain that it's something with IPsec and the cryptography that's causing the problem. Do we have compatible IKE Phase 1 policies? Do we have compatible transform sets? Do we have the correct authentication setup between the two devices? So what you and I get to do is we're going to take a look at this live environment. We have talked to the customer. They have told us that R2 is having a problem. They said they could never get it to work. R1, R4, and R3 are all working perfectly, and our job is to go in and identify what the problem is and correct the problems as we find them. So we're going to start right here on R2, and let's just do a few basic connectivity tests to verify we have connectivity over to our good friend Mr. R1. We'll start that with a ping of 15001 just to make sure we have basic reachability. Okay, so we can't even ping the outside address, the internet facing address on R1. That is a huge problem to start off with. So R2 may well ask the question, is it me? Well, let's take a look. Let's do a show IP interface brief. We'll do a pipe and say, please exclude any output that has the word unassigned in it. So it looks like gigabit 1/0 with the IP address of 25.0.0.2 is administratively down. That's this guy right here. That would definitely cause us not to be able to reach R1 if our local interface is shut down. So let's fix that. We'll go into configuration mode. We'll go into interface config for gig 1/0. We'll issue the command no shutdown. So we'll do a ping out to 15.0.0.1, and the do keyword, of course, is there because I'm in configuration mode. And now that ping looks successful. That's great. We could also do a trace route, but we know we have connectivity over to 15.0.0.1. So just for fun, let's make a road trip over to R1, and let's see if R2 has registered. So R1 is our NHS, the Next Hop Resolution Protocol server, and it appears that R3 is checked in and R4 is checked in, but we don't have R2 checking in. So we still have a problem. Because R1 is currently working with R3 and R4, we can assume that the tunnel parameters on that hub are correct. So let's go ahead and take a quick look at those, and we'll compare those against the tunnel parameters up on R2. So to do that, we'll do a show run for interface tunnel 0 right here on R1, and survey says, here are our parameters. And so here's what I would do. Literally, if I was in a production network troubleshooting this, I would take this and I would put it over into Notepad. Or if you're on a Mac, TextEdit, whatever your text editor of choice is. And then I would get the configuration off of R2. Now we know it has a tunnel interface because we saw it in the show IP interface brief. However, it could be a possibility that there is no tunnel interface, hasn't even been set up yet. But in our case, because it is set up, we could take the output from R2, also put it into Notepad, put them side by side, and compare the values. Now the parameter of IP NHRP redirect applies only to the hub. And the split horizon and the no next hop self also are only relevant for the hub. But the network ID should be the same across the board. The key should be the same. The NHRP authentication should be the same. So we want to double check that against the values that are in the tunnel interface configured on R2 to see if there's a discrepancy or a difference that's causing it not to work. So let's make a road trip over to R2, and we'll do a show run for interface tunnel 0. Again, the do keyword because we're in configuration mode. And we'll want to go through those values and simply compare them back and forth. So going back to R1 for a moment, the IP NHRP network ID is 1, and on R2, the IP NHRP network ID is also 1. So that part's good. Going back to R1, the NHRP authentication keyword is Cisco123, and on R2, the IP NHRP authentication keyword is Cisco123. And that also could be referred to as the password for NHRP authentication. Let's go back to R1. We have this tunnel key of 6783. On R1, the hub, if we go over to R2, we have a tunnel key of wait a sec, that is not 6783. So we had a little dyslexic moment there, or I did. So those do not match. 7683 and going back to R1, 6783 are definitely different tunnel keys for the GRE tunnel. So that's at least one of our problems. Let's go ahead and correct that by going into interface tunnel 0 and typing in tunnel space key space the right number of 6783 as the key. And now at least that problem has been resolved. Now if that was the only problem, we should be able to go ahead and ping to the 10.1.1 subnet. Because the GRE would be working between these two devices. It'd be protected by IPsec. We'd be running EIGRP over that, which we set up in our first DMVPN video in this course. So let's try that. If that works, that's a very good sign. If not, we'll continue troubleshooting. So let's do a ping over to 10.1.1.1. That is the host interface of R1 on that subnet. We'll do a repeat count of 1, and it says U as in unreachable. Now we might ask R2, okay R2, why is it that you can't get to 10.1.1? And the result is, if we do a show IP route, we don't have that route in the routing table. We don't know how to get to 10.1.1. In fact, I see a bigger problem, that is we don't have any EIGRP learned routes here. So one of the other questions we might ask is, okay, are we running EIGRP? That would also be a factor to make sure that we're able to share EIGRP routing information. So we'll do a show IP protocols. And the show IP protocol says, yeah, we've got EIGRP running for Autonomous System 777. These are your network statements you have. And check it out. Looks like we've learned something from 162.16.0.1. That's R1. That's our hub. However, it says the last update was like 40 minutes ago. So I wonder if that is a valid neighbor. Let's do a show IP EIGRP neighbors and just verify whether or not we really do have a neighbor. So although looking at this, it kind of indicates, hey, we've got a neighborship in place. That is old information. And here's a little tricky part. EIGRP, if the network is stable, it's not changing, there's no new information, we might not have any new information from a neighbor for 40 minutes. So this by itself may be an okay number, but the fact that we have no active neighbors, that's a problem. And a little inside scoop between you and I, the reason that was up 40 minutes ago is because when I brought this network up from our previous video, it was working, and then I injected some problems, which caused it to no longer work. So we don't have our EIGRP neighbors. And here's what I like to do for our testing. Because this is a closed track, let's go ahead and remove the IPsec profile off of the tunnel interface on R1 and off of the tunnel interface on R2, because in doing so, that will remove the whole variable of cryptography as causing the problem. And it'll be interesting to see, because if we pull off the cryptography and it still doesn't work, that means it's something else other than just cryptography that's causing the problem. So to remove the IPsec profile, let's first take a look at the tunnel interface again, so we can make sure we do the right syntax to pull it off with a show run interface for tunnel 0. And then we'll simply go into interface tunnel 0, and we'll say no. And then we'll type the entire command, tunnel protection IPsec profile, our underscore IPsec underscore profile, and that will remove that IPsec profile from the interface. We're also going to want to do that on R1. Now be warned that if we remove the IPsec profile off of the tunnel interface on R1, that's going to be really bad news for R4 and R3. But because this is a lab environment, and I'm not worried about production traffic going between R3 and the hub or R4 and the hub, I'm going to temporarily take it off. So over at R1, we'll go into configuration mode. Let's do a show run for interface tunnel 0, just to verify the right syntax. Then we'll go into interface tunnel 0, and we'll simply say no. I think that was Nancy Reagan's policy, just say no. In this case, we're saying no tunnel protection IPsec profile and the name of our IPsec profile. And now it's gone. Now if that worked, we should have an EIGRP active neighborship between R1 and R2. And we should have some routes that are showing up, at least the 10.1.1 subnet showing up on R2. So let's go back to R2. And on R2, we'll do a show IP route for just EIGRP learned routes. And sure enough, there it is. Now, I do have logging to the console turned off on both R1 and R2. So now we should be able to do a ping of 10.1.1.1. We'll do a repeat count of 1. And if that works, that verifies a lot of things. It verifies, first of all, that the GRE is working, the routing is working. We've also isolated the rest of the problem to IPsec, because by itself, the DMVPN is now working. We had a key issue on the GRE tunnel. We fixed that. And with the IPsec profile removed, R1 and R2 are happy. So to troubleshoot the IPsec, let's go ahead and put IPsec back on by reapplying the IPsec profiles on the interface. First on R1, we'll do tunnel protection IPsec profile, our underscore IPsec underscore profile to reapply that. And we'll reapply it also on the tunnel interface right here on R2. So now with that tunnel protection profile in place, if we do a show IP route for EIGRP, it's very likely that we're not going to have anything there because we lost our EIGRP neighborship due to something in the IPsec world. And so now it comes down to troubleshooting the IPsec portion of our DMVPN. Now here on R2, what I'd like to do is quiet things down a little bit by telling interface gig1/0 to take a nap, to go ahead and be in a shutdown state. And although I'm not logging at the moment to console, I do want to log to the buffer. So I'm going to say logging buffered 7, double check to make sure that logging console is disabled with no logging console. I'm also going to clear the log. So now if we look at the log in memory, it should be fairly clean. On R1, I also want to do some logging, and I want to log to buffer, and I want to log to the console that we're looking at. So we'll go into configuration mode, logging buffered at debug level, which is 7, logging console at level 7, and I'm also going to turn on debugging for crypto isocamp. Now debug crypto isocamp is very, very close to saying please debug the IKE phase 1 process. It's not literal, but it's really, really close. If we want to see the nitty-gritty regarding IKE phase 1 negotiations, this is the debug to use. I also want to point out that with IPsec for IKE phase 1, we're going to have an initiator. So in this case, when we bring up the gig1/0 interface on R2, R2 is going to be the initiator because he's trying to connect over to R1. And what I like to do is I'd like to run the debug for crypto isocamp on the device that's receiving the invitation to go ahead and do IKE phase 1. So if you're not sure which side is going to initiate the conversation, you could do debugging of crypto isocamp on both of them. But just be aware that if you're logging to the console and you have lots of clients that are connecting, that is a boatload of information. So be very, very careful on any debugs, especially if you're setting it to the console, regarding the quantity and how much content could be coming in. All right, so with that debugging in place, let's go over to R2 and let's bring up that gig 1/0 interface by going into interface config for gig 1/0 and using the command no shutdown, and that should create a flurry of debug activity over on R1 as R2 initiates an Ike phase 1 negotiation with R1. So if we head over to R1 and take a look at the output there, I don't want to have to fight this screen, so let me do a couple things. I'm going to do a no logging console. I'm going to get out of configuration mode. I'm also going to specify an undebug all. So if we scroll up a little bit to the top of this negotiation, it said in this ISACEMP debug, hey, I received a packet from 25002. It was on UDP port 500, and it came from UDP port 500. And that's the beginning of a beautiful Ike phase 1 negotiation. And if we scroll down a little bit further, here's the really interesting part. R2 sent over an Ike phase 1 negotiation, and it said, hey, here's the things I'd like to haggle with you. Remember, haggle is the hash, authentication, Diffie-Hellman group, lifetime, and the encryption. So in the Ike phase 1 proposal that was sent over, R1 is saying, okay, I'm going to compare what you offered me to my policy number 5, my crypto ISACEMP policy number 5. So it went through those and says, oh, you know what? Bummer. Attributes are not acceptable. And that means one of these things that were offered here doesn't match a policy on R1. Now, if there's multiple policies, they'll all be checked, and we're simply looking for one of these sets of Ike phase 1 policies that match. So if we have 5 different policies, only one needs to match. In this case, this is the only policy that R2 is offering. And it also says right here, the proposed key length does not match policy. So they take a look at the key length, that's for AES, and that's a really good indication of what's wrong. However, if it just said attributes are not acceptable, we could then just look at the Ike phase 1 policy or policies on R1 and R2 just to take a look at what they are. And if they don't agree, we need to make them agree. So on R1, let's do a show crypto ISACEMP policy to see what the policies are locally here on R1. And R1 is saying I'm using for my Ike phase 1 policy, which is policy number 5. I'm using AES 256 for hashing SHA, pre-shared key for authentication, Diffie-Hellman group 14, and a lifetime of 86,400 seconds. And right there, that's our problem. Because in the debug, it said that R2 offered a 128-bit key, yet our policy says a 256-bit key. That's not an exact match. And because that's our only policy, game over. So if we make a road trip over to R2 and we do a show crypto ISACEMP policy here just to verify what the policies are, sure enough, everything matches except for that 128-bit key. And that's what we need to fix. So to fix that, we'll go into crypto ISACEMP policy 5 configuration mode and we'll say encryption AES 256. So that is our syntax right here. And if we use the up arrow key a few times, it's always nice to verify that what we configured also is reflected in the appropriate show commands. So our next step is we had a problem with our Ike phase 1 policy. The attributes weren't acceptable, meaning compatible with each other between R2 and R1. Let's do a show crypto ISACEMP SA. SA stands for Security Association, and see whether or not we have an active Ike phase 1 tunnel that is working. Okay, so a couple of bad things. The deleted obviously is not a good indication. We had a security association for Ike phase 1 that was either attempting or trying to come up. It's since been removed, and if we wait long enough, they'll completely disappear from this screen as well. But they didn't get very far because it says MM no state. MM is for main mode. Now there's 2 modes in Ike phase 2, the APSec tunnel. There's main mode and quick mode. And the way it plays out with Ike version 1 is that Ike phase 1 completes, and then it goes into either main mode or quick mode for Ike phase 2, which negotiates and builds the Ike phase 2 tunnel. But here, it didn't even get that far. MM no state. It didn't even have the opportunity to kick off main mode. So these Ike phase 1 tunnels were not successful. So what I'd like to do is let's do some more debugging over on R1. So on R1, let's go into configuration mode. We'll say logging console 7. I'm going to clear the buffer as well. So if we need to go back to it, we'll have a nice easy way to find what we just did. And then let's do a debug of crypto ISACEMP. Now with that on, wow, lots of traffic already there. Let's go back over to R2. And in R2, let's go into interface configuration mode for gig 1/0, and let's shut that puppy down with a shutdown command in interface configuration mode. And just for grins, let's do a show crypto ISACEMP SA. So I'm going to kick in a little extra sauce here. Let's do a clear crypto ISACEMP and hit the up arrow key a couple times. And I just want to make sure these are both showing up as deleted. Now with the physical interface shut down, we're not going to have any really successful new communications until we bring the interface back up. And the debug is running over on R1. So on R2, we're in interface configuration mode still for gig 1/0. Let's go ahead and do a no shutdown to go ahead and bring it up. Now we already resolved the issue with the IKE phase 1 attributes, the matching policies. But because IKE phase 1 is still not successful, we're now doing troubleshooting for what else might be the problem. So let's go back over to R1. And on R1, let's do a no logging console to stop the output to the screen. I'm also going to turn off debugging. I think we have more than enough to go ahead and go with what's on the screen. So let's scroll up a little bit and see what's interesting in this output. Now, I love this part right here. This is the IKE phase 1 negotiation. R1 offered all of these attributes. And R1 said, hey, attributes are acceptable. So we've now verified that we have a compatible IKE phase 1 policy on R1 and R2. So let's scroll down and see what else we find that may be interesting to us. Now what we're not seeing in this output is any positive messages about IKE phase 1 completing successfully and kicking off quick mode or kicking off main mode to establish the IKE phase 2 tunnel. But what I do see is this one right here, which is a problem. So this isn't even a debug message. This is a console message. It's a level 4 message. And it says that the IKE message from 25002 failed its sanity check or is malformed. Either of those is a problem. However, I do know what causes a sanity check failure for IKE phase 1. And that is, let's say that they both agreed that they were going to use pre-shared keys for authentication, which if we scroll up a little bit, they agreed to right here. If, however, we had misconfigured IKE phase 1 authentication keys, that would cause that console message indicating there's a sanity check failure. And that's this guy right here. And then once it fails, they're just trying over and over and over again to establish and set up the IKE phase 1. And if the key is incorrect for the IKE phase 1 policy, it's going to fail over and over and over again. And I guess that's where the sanity thing got its name from, where the definition of insanity is trying the same thing over and over and over again, expecting to get different results. You and I need to change the keys if that's the problem, if we're going to get past the sanity check failure. So on R1, let's do a show crypto ISAKMP key to see what we have configured as a key for the IKE phase 1 policy here on R1. And this says I'm using a wildcard and the key is Cisco123, which means that key of Cisco123 should work with any other peer. If we make a road trip over to R2 and ask that same question, please show us the crypto ISAKMP key, it also should be Cisco123. And it could be either with the specific IP address of R1, which is 15001, or it could be using a wildcard, which it is, and that and that's our problem. This should be Cisco123, not just Cisco. So we need to correct that. Now we want to make sure we get the syntax correct as well. So I'm going to do a show run with a pipe and say, please show me the section regarding crypto. And by doing that, I can look at the exact syntax of the key. So crypto ISAKMP key, Cisco, address, and wildcards. And when we configure this, we just put in 0000, and it automatically put in the trailing 4 zeros for us. So this key of Cisco should be Cisco123. The iOS router doesn't like it when you try to put in a key for an existing peer. So what I'm going to do is I'm going to remove that key, which is a key that we can use with anybody, and then I'm going to put in the key again correctly of Cisco123. So now that we have that key defined, and we've given a few seconds for IKE phase 1 to hopefully negotiate in the background, how do we check that? Let's do a show crypto ISAKMP SA, again, SA being an acronym for Security Association. And that still looks like a problem. Let me share with you another command that I really, really enjoy. It's show crypto engine connections active. And that will show us like a bird's eye view of our IKE phase 1 and IKE phase 2. Now I want to point out something. Between this command of show crypto ISAKMP SA and this command of show crypto engine connections active, we actually have a new connection. This was connection ID 1029, and now we're at 1030. So let me hit the up arrow key a couple times. And let's do a show crypto ISAKMP SA again, and there we go. So we now have a happy IKE phase 1 security association. So QM idle from an IKE phase 1 security association perspective is a beautiful sign. And the lifetime for that IKE phase 1 tunnel should be approximately 1 day. And if we want to see the details for that, we can do a show crypto ISAKMP SA and the keyword detail after it, and that verifies it. So we're using AES, SHA, pre-shared key, Diffie-Hellman group 14, and the remaining lifetime is 24 hours minus about 3 minutes, because that's how long the tunnel has been up. So now the question is, do we have a good IPsec tunnel, meaning an IKE phase 2 tunnel? Has that come up? And we can simply ask the router to tell us that by doing a show crypto IPsec essay to see any security associations for IKE phase 2. I'm going to hit the space bar. So in our case, regarding ESP, we have no inbound or outbound security associations. So with IPsec, it actually treats them as two unidirectional paths, one going to the destination, one coming from the destination, regarding IPsec. So we already verified that we have a good IKE phase 1 tunnel, and that we verified with the show crypto ISAKEMP essay. But regarding a functioning, working IPsec tunnel between R1 and R2, we have nothing. So again, here's the command I'm using to verify our IPsec or IKE phase 2 information. And this is saying I'm willing to encrypt and decrypt respectively between these two pairs of IP addresses if the protocol is 47. But here we have packets encrypted and packets decrypted. Nothing. And below, in the section where it showed us the security associations, there was none for outgoing ESP traffic and none for incoming ESP traffic. Which means effectively we don't have IPsec working between these two devices. And also, while we're right here, if IKE phase 2 was working maybe partially, and it showed, for example, 2,000 packets encapsulated, 2,000 packets encrypted, but for de-encapsulation it showed 0, and for decryption it showed 0, that would mean that we're sending traffic all day long. We're encrypting it, but for some reason we're not getting any encrypted traffic back coming in from the peer at the other side. So let's troubleshoot the IKE phase 2. Let's go over to R1. And on R1, let's do a clear log. Just so if we have to go to the memory, we can not have to look at all the debugs we've done so far. And I also want to see what we currently have debugging. So because I've turned debugging off, I want to go ahead and turn on debugging for both ISAKEMP, which is mostly phase 1, as well as more details on the IKE phase 2, which is debug, crypto, IPsec. And then with those both together, let's do logging back to the console. Let's go back to R2. On R2, let's go to interface configuration mode for gig 1/0, and I'm simply going to shut down that interface. So on R2, let's go ahead and bring the interface back up. Let's go back over to R1, and the debug messages are pouring in. We'll give it just a moment. And that's probably enough. We'll go ahead and do a no logging console. I'm also going to turn off debugging on this device. So here's our IKE phase 1 information again. So that's great. IKE phase 1 was successful. It's doing some checks regarding NAT, because if we are going through NAT, it might automatically kick over to NAT traversal, which adds a UDP port 4500, with the intention of going through devices that support PAD but can't handle protocol 50 for IPsec. So in our case, because we're not going through NAT, it's not going to do anything about adding on a little shim UDP header in front of the IPsec packets. And if it did, it'd be UDP port 4500. But in this case, there's no NAT involved, so it's a moot point for our topology. And look at this, IKE process complete. That's fantastic. So IKE phase 1 had a successful run. Now this next portion of our output, even though it's under the flag of ISAKEMP, which is often just thought of as IKE phase 1, ISAKEMP stands for the Internet Security Association Key Management Protocol. And a lot of the automation and negotiations that are done for both IKE phase 1 and IKE phase 2 are done using the features of ISAKEMP. And this negotiation right here is regarding our IKE phase 2 policy. Inside of our IPsec profile that we applied to the tunnel interface, we called upon a transform set. And in that transform set, we had specifications for things like the encryption that we're going to use, and the HMAC method we're going to use, and the mode we're going to use. So for example, right here we have transport mode, which we specified. And we did not specify a duration regarding a lifetime. So it took the defaults of 3,600 seconds. And here it's saying that the proposal is saying HMAC MD5. When we configured R1, we used HMAC SHA. Definitely. Now, normally, here's what I would expect to happen. I would expect this to come back and say attributes are not acceptable. This is regarding the IKE phase 2. Because the proposal of HMAC MD5 doesn't jive with R1's HMAC of SHA. Again, that is surprising to me that it doesn't show that attributes are not acceptable. However, even though in the debug we have this attributes are acceptable, this last line shows us that IPsec policy invalidated proposal with error 32, which in this case is directly related to our proposals for the IKE phase 2, not being congruent with each other between R1 and R2. So to verify that, let's take a look at what is currently on R1 regarding the transform set. We'll do a show crypto IPsec transform-set, and that'll tell us exactly what's there, what we've configured, and also what the defaults are. Sure enough, currently we're using transport mode with ESP256, AES, and ESP SHA HMAC. And that was not the proposal that we had offered to us by R2. R2 did offer us a key length of 256 for AES for the IKE Phase 2, but it's offering MD5 HMAC instead of SHA HMAC. And that's ultimately why IPsec Phase 2 failed. We can also issue the command show run pipe section crypto if we want to see the syntax for our transform set. So here's our transform set right here. So we need to make sure that R2 is using a compatible transform set. The name doesn't have to be the same, but the ingredients regarding the encryption and the hashed message authentication code, that needs to be identical on both sides. So back to R2, let's go ahead and do a couple things. Let's do a show crypto IPsec transform-set just to verify that it is incorrect with what R1 has. Then we'll do a show run pipe section transform to make sure we know the correct syntax to put in the corrections. So in our case, we're just going to overwrite the old transform set called our set. For the new version, we're going to use AES 256 and SHA HMAC. I'm also going to make sure that the mode transport is specified, and that should match what R1 has as well regarding IKE Phase 2 policy. So now, if that was the last nail in the coffin, if that was the last problem regarding the IKE Phase 2 policy not matching, we should have a few basic things working for us. Number one, if we do a show crypto ISACEMP SA, we should have a beautiful IKE Phase 1, which we corrected earlier. That's great. However, now for IPsec Phase 2, if we do a show crypto IPsec SA, we should have some functioning security associations. So I've hit the space bar and scroll up just a little bit. Here's our inbound ESP security association, and here's our outbound ESP security association. And if we scroll up a little bit further, and here it shows us that we've had packets that we've encrypted and sent over to R1. Also, we've also received packets, and we've decrypted them and de-encapsulated them from R1, which implies that this IKE Phase 2 tunnel, the IPsec if you will, is functioning between R1 and R2. If we use the command show crypto engine connections active, which is again one of my favorites, gives us a good bird's eye picture of what's going on, it should show us our IKE Phase 1 and IKE Phase 2. So here's our IKE Phase 1 information. And by the way, it does increment numerically. So this reminds me of Thomas Edison with the light bulb. When somebody asked him, hey, how's it feel to fail so many times? He said, I didn't fail so many times. I just figured a whole bunch of ways it didn't work. Well, this was the 1032nd IKE Phase 1 tunnel that this router has brought up, or attempted to bring up. And this one is successful. And the IKE Phase 1 tunnel is just the control plane, if you will, for IPsec between R1 and R2. The actual data, the transit data, is going to be sent over the IKE Phase 2 tunnel. And here it's representing the IPsec based on their connection ID. So for example, connection ID 20 right here, let me get a different color. Connection ID 20 refers to this flow of traffic. And 19 is simply the other direction. And we can tell right here based on encryption that 20 is the outbound flow because we're encrypting traffic and sending it. And number 19 is the inbound flow because we're decrypting that. And just for fun, if we wanted to try to ping R3, maybe back to this 10.33 network, that would be a great way to verify that the whole DMVPN operation is working correctly. So let's do a ping out to 10.3.3.3. I'll source it from our 10.2.2 local network. We'll do a repeat count of 1, and it made it. Now that initial traffic very likely went through the hub. However, in the background, all the NHRP resolutions happening. That's going to allow R2 and R3 to discover each other's respective NBMA addresses, the reachable ones on the internet. And once they do, they can start sending traffic directly to each other, which will cause IKE Phase 1 negotiations to happen between each other. The IPsec tunnels will be then set up, and we'll have a whole bunch of new IPsec security associations. So let me do one more ping just for fun. And then if we use that command of show crypto engine connections active, check this out. And if we want to see which of those tunnels are really being used, if we sent more traffic, for example, let's go ahead and send 2 more pings to 10.3.3. And then we use the up arrow key. These are the counters that are increasing. Now we had some increased counters for both of those. Let me do one more thing. Let's do that command one more time. So the traffic between R1 and R2 is increasing based on background traffic that I'm not causing. But if we send one packet between R2 to R3, we should see these counters go from 3 and 4 up to 4 and 5. So we'll send that one more ping, and sure enough, we have the counters increasing, And then we might ask, okay, why is it that we have two brand new Ike Phase 1 tunnels? And the reason is because these two routers, these two spokes, once they had NHRP done and they resolved each other, they both initiated Ike Phase 1 tunnels with each other. They both succeeded, they were both accepted, and that's why we have two Ike Phase 1 tunnels between R2 and R3. They're both not needed. One would do the trick, but because they both initiated tunnels and they both succeeded, that's why we have two sets of Ike Phase 1 tunnels between R2 and R3. And one last command I'd like to do is let's do the show DMVPN detail command. So the first part of this output, show DMVPN detail, is going to provide our mappings between the NBMA addresses, that's the reachable addresses on the internet, and the GRE tunnel addresses associated with the tunnel interfaces on each of those devices. And then below that, in the crypto session details, it's going to give us information regarding the Ike Phase 1 tunnels that we have in place and the Ike Phase 2 tunnels that we have in place. So this first one is between us, R2, and 35003. The next one down here is between us and R1 at 15001. I have had a great time in troubleshooting with you in this video. Here's what I'd like you to do. I would like you to lab this up and practice with it. Now, what I've done is I've created a document called troubleshootingdmvpn.txt. I've included it with the Nugget Lab files for this course, and it has several things in it. Number one, if you've gone through the previous two videos with me where you've built DMVPN and you added IPsec on top of it, first of all, congratulations. You're awesome. Way to go. Secondly, if you'd like to go ahead and then troubleshoot the DMVPN, I have three major sections for this document. The first is the configuration that you can add to R2 that will break DMVPN 4 different ways. And those are the problems that we just resolved together using troubleshooting in this video. The next part of this are the immediate solutions to fix R2. And then if we scroll down a little bit further, I have the exact steps that we went through in class regarding the troubleshooting. The show commands, the verification commands on both R1 and R2, including the debugs. So if you want to walk through that troubleshooting on your own, which I strongly recommend you do to practice with it, you can use this text in a couple different ways. Number one, to remember the commands and to practice them. And secondly, to remember the logic of what we would check for, how we would check for it. And having you, my friend, practice with the hands-on and doing the troubleshooting is going to make you that much better when you have to troubleshoot this in the real world. So please enjoy the process, enjoy the practice, and watch your skills get better and better and better as you do the hands-on. Again, I've had a great time in this video. I'm so glad you joined me for it. I hope this has been informative for you, and I'd like to thank you for viewing.